Okay, so question 58, propose a mechanism for each of the following reactions. So there are a couple here, and I'm just going to do the first one again just to kind of get you thinking along the right lines. So sub-question A, it's basically very simple in terms of what we have to do. The difficult part is going to come in making sure that you keep track of where all of your carbons are and what happens to everything. So it's very easy to mess this kind of thing up. The linchpin of this problem, I think, is probably the identification of the mechanism. So you know that you're doing some kind of substitution reaction here. You know that you're getting rid of this bromine at some point, and you know that you're replacing it with this hydroxy group. So what we're going to do is first identify the mechanism. So we're doing a substitution. The question you should ask yourself, SN1 or SN2? So this reactant slash solvent is the key to this. You should take from this that water is the solvent as well as the reactant. So this is a solvolysis reaction. So solvolysis normally, preferentially, will go for an SN1 reaction. And also the fact that this is a very weak nucleophile should in general preclude you from thinking about this as an SN2-esque mechanism. So because of that, we need to start thinking in terms of SN1. So we're going to start to think about this mechanism in terms of SN1. Okay, so the first step for SN1 is always going to be the dissociation of the halogen from this carbon-halogen bond. So that's the first step, and that's pretty much all you should do. So again, whenever you're drawing mechanisms, try to limit yourself to 1, 2, maybe 3 steps at a time. Once you move to multiple steps happening simultaneously, it's really difficult for me to understand what you're trying to say, and for anybody in particular to understand what you're trying to say. You have to walk the audience through your train of thought so they can see how you're trying to approach the mechanism. Okay, so little small changes and we'll get there eventually. So we're not doing anything to the four-membered ring. All we're doing is we are pushing off that bromine and we're going to get a carbocation as our intermediate. Okay, so here we have our carbocation. I'm not going to draw this hydrogen anymore just because it's implicit. So thinking about where we're starting and where we're going, we're starting off with a four-membered ring and we're ending up with a 5. So that should indicate to you that we're going to be doing a ring expansion. So we're going to be doing a ring expansion, and we're going to be doing that by a carbon shift. So we can do hydride shifts or we can do carbon shifts. Okay, so the way to do this is let's just go ahead and start numbering things. So I'm just going to go ahead and number 1, 2, 3, 4, 5, 6. So we have 6 carbons here. Thinking about how many carbons we have here. 1, 2, 3, 4, 5, 6. Okay, so let's keep that in mind. So we know we have to do the ring expansion. Which bond do we want to break? Do we want to break the 3-4 bond or the 3-6 bond? And to answer your question, it doesn't really matter. We could do either one, and either one would suffice. At the end of the day, we'll get the same answer. Okay, so let's go ahead and break this 3-6 bond. And we're using the electrons that used to be in the 3-6 sigma bond to make a new sigma bond between 2 and 6. Okay, so that's what we're going to do. We're going to make a new bond, and we're making it between 2 and 6. So overall now we have that 1, 2, 3, 4, 5-membered ring. So instead of trying to redraw this in a specific way, just redraw a 5-membered ring and it'll make things a lot easier on you later on. Okay, so 5-membered ring. And then let's just go ahead and start numbering. Does it matter where you number? Nah, not really. I'm just going to start randomly numbering. So I'll number this as, I don't know, I'll do this as 6. So this will be 6, this will be 2. So if this is 6 and 2, 6 and 2, the next along the line must be 3. Then the next along the line must be 4. Then the next along the line must be 5. So right now we're actually missing something. We're missing another carbon. We know we have 6 total and I'm missing 1, so I need to go back and add it where it needs to be. So now that I've numbered, it's very convenient. I know the carbon that I'm missing is this carbon 1, and I know carbon 1 was attached to 2. Okay, so carbon 1 was attached to 2, so this is 1. Okay, and right now the issue is where did that positive charge go to? So what you should look at, you should really try to focus in on the carbons where bonds were made and bonds were broken, and that's really going to help you out. So thinking about these three carbons in this general area, 2, 3, 6. These are the carbons where all the bond making and bond breaking is occurring. So probably what's going to happen is we're not going to have that positive charge on 2 anymore, but let's go ahead and double check. So we used to have a positive charge, but I'll also go ahead and redraw that original hydrogen that was there just to make things easier. So originally we had 1 hydrogen attached. So now we have to ask ourselves how many hydrogens are attached to 2. If it's 1, then the overall charge is neutral. If it's 0, then the overall charge should be positive. So right now we know that we have 1 carbon, carbon 1, and we know that we still have another hydrogen, so right here. So that positive charge is no longer on 2, it's somewhere else. Okay. So thinking about 6 had 2 hydrogens on it, and carbon 3 had 1 extra hydrogen on it. So now if we think about carbon 6, 2 hydrogens here, it's impossible for 6 to have a positive charge. Carbon 3 only had 1 hydrogen right here. Okay, so thinking about the number of bonds that used to be on carbon 3. Carbon 3 used to have 1, 2, 3, 4 bonds. Once we broke that 6-3 bond, that bond's gone. So we're not adding anything to 3, we're only removing things from carbon 3. So because of that, we now have a 4 - 3 situation, so we're going to have a positive charge on 3. And this is totally fine, there's nothing wrong with this at all. The only thing we have to do is figure out a way to get from this carbocation to something where we have a hydroxy attached. And that's our next hint. Okay, so our hint is going to be we need to add a hydroxy. We're using water as our solvent, our solvolysis solvent. So let's go ahead and add a little bit of water. So we have a lot of water in solution. Water is a poor nucleophile, but it can act as a nucleophile nonetheless. So this is a very simple step. All we're doing is the next step in it as a traditional S-Syn reaction, we're making a new bond. Okay, so we've made a new bond between 3 and the hydroxy group. So I'll redraw everything. Redraw my 5-membered ring. We've got a methyl group here, and now we have our water attached to carbon 3. Okay, so now let's go ahead and put our water. This is the step where people usually make a mistake. Okay, people usually what they want to do is they want to just put that water on and neglect the second hydrogen on this oxygen. So we have 2 hydrogens here. People usually take this step and they'll go and say, well, something happens and this is what you get because this looks like this. And that's true. That's what you want to get. But if you just say that you add the water here and you get this, you're neglecting part of the story that you should be telling. So here you have 2 hydrogens here, and here you only have 1. So where'd that other hydrogen go? This is important information that you need to convey to your listeners or your readers. Okay, so you can't just do that. You can't just skip a step. Okay, so you have the hydrogen, you have a positive charge. So the question you should ask yourself is, well, how do we get rid of that positive charge? And how do we make this look more like this? Because we're almost there. This is a very, very simple step, and it's almost, it's almost too much to add it, but it's still an important step to show because it's, it tells the complete chain of events about how you got from point A to point B. And all we're doing is we're going to use water now, not as a nucleophile, but also as a base. So we're going to have a lot of water in this reaction, plenty of water left over to pull off a proton and give an extra lone pair to this oxygen. And as soon as we do that, we're going to finally form the final product. Okay? And all you have to really do is, it doesn't look like this is the same as this, but if you numbered everything, this is 3 and 2, 6, 5, 4. All you really have to do is rotate this molecule clockwise by a little bit. And this would be 3, this would be 2, this is 6, 5, 4. Okay, and that's the end of that problem. That's really as simple as it is. But just don't forget this, this third step. It's very, very important. It's very easy to do. It's also very easy to mess it up. Okay, but yeah, that's pretty much it. All right, next question.